It's great to see you. Well, right now we are going to get ready to have our annual special meeting to vote for this coming year's board of directors. Right now, we are passing around sign-up lists for all active members of Madison Astronomical Society. Put down their names because we need to verify, we need to have record that we do have, per the bylaws, a quorum this evening. And as soon as we can verify that we have a quorum present, I will call a brief Robert's Rules of Order meeting to order. While that's going on, I'll go over through a few announcements. This coming Saturday, a week from tomorrow, May 20th at 7:30 p.m., we have a scheduled star party at Yana Research Station. So this is an opportunity for all members who haven't been to Yana Research Station yet, or for all people who love hanging out there during the new moon and doing some stargazing. Weather permitting, at 7:30 p.m. we'll have a star party. Another very special thing coming up at Yana Research Station, we are organizing a picnic there to kind of celebrate before the renovation begins on Saturday, July 8th, tentatively planned, with also a tentatively planned rain date on Saturday, July 15th. Yes, Jurgen?
Are there people who have not signed either of the two sign-up sheets who are members?
So yeah, in the past we've served food there. People have brought dishes, and we kind of shared food and beverages. And then, weather permitting, we've had stargazing after the picnic. So I have begun to form a planning committee for that. As of now, I've got Martin, our observatory director, and Chris Zeltner.
I think Martin and I talked, I think we have it kind of figured out, but I was looking for volunteers day out.
Yeah, we want to figure out what kind of volunteers we want, and what things volunteers can do. Right. And we could have a brief Zoom meeting to kind of draw up a plan, and then we'll make sure that we get all the volunteers we need. So yes, you're going. Okay. All right. And one more thing. I think we've got plenty of time. Another thing coming up in July, right after that, will be a very special, for those of us who have participated in Moon over Monona Terrace in the past, in appreciation for all the great events that Madison Astronomical Society has helped put on there. The Monona Terrace has offered us an opportunity to raise some money for Madison Astronomical Society by hosting an adult beverage oriented stargazing party called Cocktails and the Cosmos on Friday, July 21st. Kevin, did you want to talk?
I was going to say, because it's the summertime and the sun sets around if I could. Because it's in the summertime and the sun sets at around 8:30, that's about the time they're going to let the guests in. We are working with Misty at Monona Terrace to try to see if we can actually stay up until midnight.
And I did see an email from her saying, that midnight.
Oh, it is good? Okay.
Run till midnight.
So we're going to be on from like 8:30 to midnight. We're probably going to be have access around 6 o'clock in the evening so we can get to the roof and set up. But we're hoping to have at least 15 scopes or stations set up on the roof.
Or 8. I think last time we planned this, we had plans for like 8 telescopes, and rather than having a free-for-all, we had specific objects planned ahead. But more telescopes than that would be okay. Again, kind of since it's a light pollution challenged environment, I think a couple of volunteers have expressed interest in doing electronically assisted observing, which is great. And I'm bringing a large aperture telescope with some light pollution filters that I've observed galaxies with the full moon out, so it should work. Yeah.
Yeah. It's good setting.
Yeah. Crescent moon setting, really. Okay.
Yeah, and we also will probably do a display similar to what we did in Moon over Monona, where we had displayed a lot of people's artworks, and we might be expanding on that. One other thing we're talking about doing too is taking some of that artwork and actually making prints and doing a silent auction to raise the money too.
So yeah, for those of you who have art, photography, astrophotography art that you might consider donating to the effort, we'll stay tuned and we'll have details to announce in the near future. Does anybody have any questions about any of that? Yes, Bob? Yes, Friday, July 21st. All right, so, oh yes, Chris.
Do we want to think about if somebody would help me, I would be willing to run the 16-inch Starmaster.
Yeah, that would be really great. Yeah, keep that in mind. So I'll be running a 14-inch Schmidt Cassegrain. I think if other people are available, we might be able to really, in spite of the light pollution, we should be able to put on a really great show. All right, so I guess I have heard word that we, Jurgen, our secretary, can you confirm that we have a quorum to have a meeting of the Madison Astronomical Society General Assembly?
Yes, we have 128 members, being 15%, which is 20, and we have more than that.
So we have more than 20 people here, including at least 3 members of the board. So we do in fact have a quorum. So at this moment, at 7:16 p.m., I'd like to call to order the meeting of the Madison Astronomical Society General Assembly. The meeting is in order. The only item of business is the annual election of our board of directors, as shown on the dry erase board over there. I have listed the slate of candidates that was announced a little over a month ago and re-announced in our announcements this last weekend. In addition to those slate of candidates, we are also open to nominating any volunteers or alternative candidates for those board positions shown on the board. For those of us who need to listen, I'll announce the list. For this year, I will be returning as president. Vice president, again, will be Kevin Santoulis. Again, we'll have Jurgen Petau as treasurer. Secretary will be Dan Hislop again. Martin Mika will continue as the observatory director, and we have 2 new at-large board members joining us, Jack Fitzmeyer and David Leapart.
Can those 2 identify themselves if they're here?
There's David, and there's Jack. Thank you so much for volunteering your time this year. And they've already given us some very valuable contributions. Is there any discussion or comment, or are there any additional nominations? Here, oh yes, Kevin?
I was going to say, unless someone objects, I would like to move that we accept that slate of nominations and with a voice vote to vote yea or nay on the whole slate.
Okay, we have a motion by Kevin to approve the slate of board directors and a second by Win Wacker. Is there any further discussion? Hearing none, all those in favor of the slate presented for the board of directors for this coming year of Madison Astronomical Society signify by saying aye. Aye.
Thank you.
All those against signify by saying nay. Hearing none, it is the judge of the chair that the motion carries. With there being no further business, do I hear a motion to adjourn the meeting? There was a motion by John Rummel to adjourn and seconded by Win Wacker. All those in favor of the motion signify by saying aye. Aye. All those against signify by saying nay. It is the judgment of the chair that the nay votes were insufficient to override the yea vote. So, hearing no. All right, so the meeting is adjourned at, now I can't read my watch. It looks like we're at 7:19. 7:19. All right, and Dan, our secretary, do we have the meeting notes recorded? Yep. All right, and the meeting is closed. And I will go back into announcements mode and try to think. We talked about all sorts of neat things. I think we got through everything. Is there anyone else here that is not a member and would like to introduce themselves? Yeah, everyone here looks like a familiar, friendly face to me.
I had no meeting before.
Oh, yeah, if you haven't, feel free to introduce
I'm
yourself.
Bernie Rip. I went to a meeting last fall, but haven't been to one since. New knee, foot surgery.
Oh, how's that doing? How's it feeling?
Now back to work.
Great to hear.
But actually bought a used telescope tonight too before I came.
Oh, what did you get?
It's an old one. It's a Meade 8-inch LX. I forget. I haven't had a chance to even look at it. I picked up just a couple hours ago and haven't had a chance to pull it out and look at it even. But
And you're here?
Well, it's raining.
looking for help on how to set it up and everything.
Oh, that's why it's raining.
And that might be kind of an idea. That might be kind of an idea we have for planning the picnic. Because I know we've entertained having a little bit of a swap meet, an idea for having a swap meet, which is one idea, and also having a telescope clinic would also be another good idea.
And actually, Lawrence, if I may, just for a minute to elaborate on that swap meet, I was going to send out an email when it became official, but for some time we've been looking through our inventory at YRS, and there are a lot of scopes that are not being used a lot. There are also some that are project scopes, so if anybody is a DIYer and wants to get something on the cheap that may be a little used and abused, but might turn into something good, we are looking to downsize our inventory at YRS and hopefully use the proceeds toward the improvement at the club, as well as buying some newer scopes for members to use. So stay tuned, I'll provide details on that when we get the picnic finalized.
Thank you very much, Martin. And yeah, for those folks who are members, you know, it might be an opportunity if you have an extra eyepiece or something like that. You might find a good new home for it. So.
Bring your own stuff by all means, and feel free to swap with members.
Yes, Rick.
I just wanted to ask of the membership, please don't tell my wife about this, or she'll show up with a truckload of Astro stuff. I'm begging you.
Rick, you've got a plane, just fly it far away.
Wait a minute, is she watching the video?
Remember, this is the guy who shows up a moon over Minota with 3 or 4 telescopes.
Are we not telling her so that you can come home with a truckload?
That would be bad.
And just as long as we've got a little bit of time to fill out, does anybody have any stories of recent observations or astronomy news that they would like to share?
Oh, I did get to see that set of northern lights on April 23rd.
Oh yeah,
Those were phenomenal.
I could tell from the pictures some members shared that it was really a phenomenal show for those who weren't ruined, whose parade wasn't ruined by the clouds or anything. All right. Well, next month, I'll just give you a little bit of details about next month's meeting. Oh, yes, Jurgen?
I was just going to say, there was a thing in the newspaper that proved that went off to Pluto. They're apparently, instead of going to examine other objects out there, they're going to direct it to simply move out to space and look for interstellar space again.
Oh, really? So, yeah, the probe that went by Pluto, was it? It's just going. They're reassigning it to have a mission to, when it drifts out of the solar system, just to look for measurements of interstellar space. Like
Actually, they were talking about splitting time between looking at Kuiper belt objects and looking back at the sun and making observations towards the inner solar system. I'm not quite sure why they want to do that, but they might be trying to assess how the sun appears variable, from those kinds of distances.
Very interesting. All right, our next meeting will be on Friday, June 9th, and we're going to have a guest presentation titled "Launching the Future Astronomer: Innovation in Physics Education." John, would you like to share any details about that presentation?
So the June talk is by a physics professor named Duncan Carlsmith. Duncan has never spoken to this group before, and I can only tell you that based upon my phone conversations and emails with him, he has about 3 million ideas a minute. So I really have no idea what he's going to end up talking about, but it's going to be really good.
Thanks, John. I thought it sounded very fascinating. Thanks for arranging that guest speaker. And I also have seen online a little bit of chatter about plans for next April. If people here planning to travel to see the total solar eclipse? Yes. Yeah, where's it? Oh yeah, yes.
Yeah, we're going down to Texas. Actually, this is the biggest reunion of my family that has ever existed. We had to get a huge house to house everybody. We're just a little bit outside of Austin. So we already have the house reserved, and it's right in the middle of totality.
Oh,
so we don't even have to go much of anywhere. We could just maybe just go into the backyard and see the total eclipse. Of course, the last total eclipse, where I took part of my family, a small part of my family, and that's why we're having everybody come, because everybody now wants to come. Because we went on an adventure. What happened was that we had plan A, B, and C as to where we would go, where we would travel to. Plan A, B, and C, all of them got clouded out. Plan D, or whatever you want to call it, was get on this one road and go as fast as you can down the road with my person who was looking at the clouds and another person who was looking at the roads, and just tell me when I got to where I needed to get to, which happened to be Cairo, Nebraska at that point in time. So we saw it with 100 people in a baseball field in Cairo, Nebraska. So, but I had like about 6 or 7 cars following me, because every time I left one of the places, some of the people I talked to, they decided they wanted to follow me, and then more people.
Our nephew's in Austin, so we may be down there with you.
Oh, yeah. Austin's got this great place to be for that, because it's not far away. Yeah.
And if it's anything like the last one, you might, if we find a Piggly Wiggly on the line, because in Tennessee there was they were giving out T-shirts that says, "I saw the eclipse at the Piggly Wiggly."
Oh yes, I actually did get some T-shirts. I actually have T-shirts about where we saw the eclipse, which I thought was kind of interesting.
It does not hurt to plan ahead, because I think for the last eclipse I went to a campground in Glendale, Wyoming, and the people who tried to leave, some of the people who tried to leave right after the eclipse happened, they wound up having to return because the interstates were just all jammed closed. Yes, Martin?
So is the consensus on the best place to go Texas? Because I've got a UV camera, an IR camera, and a spectrograph, and they've got to do a lot of work in a very short amount of time.
Yeah.
So Texas it is? Okay.
Yeah, I believe, Martin, you said last time you attempted to do some measurements on...
I did. I just didn't have enough time. It was my first eclipse, so I was so wowed by it. I did get some spectra, and then all my camera settings were messed up because I was just so awestricken that when I came down and started trying to take data, I had about 20 seconds left. So this time I'll try to prepare better. I told myself, well, you get another chance in a couple of years.
Great. We look forward to your results.
I just want to ask kind of a general question about eclipses. If you happen to be not so lucky to get to a place where there's clear skies, but you're still in the path of totality, I mean, say it's cloudy wherever you are, is it still going to get dark? Yeah. See, that would be good enough for me, I think.
Yeah, and it can be a bit of a thrill, because I know what happens with animals, and my own experience was, I felt, as soon as it went dark, I felt the onset of an anxiety attack coming on, and knowing that that's the sort of neurological thing that's natural to happen, I reminded myself to take deep breaths, and then I enjoyed the eclipse.
The one thing I remember about, we were in a fairly warm place in just north of Chattanooga, and we were out in the middle of a field. It was a very sunny, very hot day. It was perfectly clear. We had perfect conditions. As soon as the totality hit, you could feel just a breeze of cold air come in, and that was weird.
And it wasn't from the group of witches behind us.
Right. There were a bunch of witches out there having some type, yeah.
As one does.
All right. It looks like it's 7:30, so it's time to introduce our guest presenter for the evening. John?
So I am very happy tonight to introduce Dr. Ellen Zweibel. Ellen has been at the University of Wisconsin for about 20 years, teaching in both physics and astronomy research, very active. I can see that she's probably going to say a little bit about her group. Ellen was a guest speaker for us last about 10 years ago, so it's about time we have her back. Looking forward to her talk. Ellen does specify that she loves questions. She doesn't want you to wait until the end. If you have a question, I'm going to have this microphone with me. Raise your hand, and I'll get to you with the microphone, and we'll wait till Ellen takes a breath or something, and then we'll let you interrupt with your question. So everybody give a very warm welcome, Ellen Zweibel.
Thanks. Can everybody hear me? I think I'm mic'd. That was the first technological challenge of the evening. So I'm really happy to be here. It made me wish that, not for the first time, that there had been an amateur astronomy association in the small town in New Jersey where I grew up, but there wasn't, and so I got to kind of dream my own dreams. And I guess I'm kind of living them now. So to set the stage for my talk, this is about observing the universe with 4 senses. So you're all familiar, you're all pros when it comes to light. Let's see, do I have my laser?
Can you use your pointer on the computer?
I probably can, but I'm very irritated because this worked beautifully in my office.
Well, the YouTube won't pick up.
Oh, right. Oh, this is on YouTube? Yeah. Okay, I was not aware of that. Okay, so can you all see my cursor? Yes. So I know you all know about electromagnetic radiation. I'll go through that quickly. This is just a schematic wavelength plot. The shorter the wavelength, the higher the energy, the higher the frequency. This is towards gamma rays. And then we go down to this tiny interval, which represents what we can actually see, the visible part of the spectrum: infrared, microwaves, and radio. But we have 3 other important messengers that we're beginning to unify to achieve, I think, an unprecedented level of understanding of some of the most energetic and mysterious systems in the universe. And those 3, actually, this is not in the order in which I'll discuss them, are gravitational waves, cosmic ray particles, which we've actually known about for a long time, and cosmic neutrinos. So I'm going to go through them and then give you some examples of the challenges and levels of understanding that we've achieved with these messengers. But I want to say, before going any farther, in case I forget, that I think how far we've come is really a test. It's really a human triumph. It's really a testament to human ingenuity that we've developed the technology to access things that we could never see before, and the theoretical tools to at least begin to understand them. So these are some of the past and current practitioners. Up here in the upper left-hand corner is Rourke Hoppeger, drinks a lot of coffee. I'm not going to talk about his work today. And my most senior colleague, Francis Halston. By the way, Duncan Carlsmith is great. He presides over garage physics in the UW Physics Department, which is exactly what it sounds like, except it's in the basement, but it's everything you wished you had in your garage. Miriam Foreman was very important to me growing up. I met her when I was an undergraduate student. Jake Waddington, real pioneer. Eun-Suk So, I believe the first woman to lead a cosmic ray mission, NASA mission. So yeah, they're great people. Okay, so let's say a little bit about the electromagnetic zoo. So we talked about energies and frequencies, but I want to go over what processes tell us we can learn about from observations at different frequencies. So this is the familiar cartoon of an atom, and we see the electrons in their valence states, and transitions between these quantized electron orbitals are typically kind of in the infrared, visual, or ultraviolet range. It turns out that atomic nuclei also have energy levels, although that's not very well depicted here, which kind of looks like a cluster of grapes. But it's possible for an atomic nucleus to also make a transition to a lower energy state, and that will typically emit a gamma ray, possibly some other particles. So the gamma rays are characteristic of nuclear transitions, and the infrared, optical, and ultraviolet are typical of electronic transitions. And then there are these very, very weak transitions, and I've depicted one here. So this is a hydrogen atom, and it turns out, so electrons spin and protons spin, and it turns out that if the spins are aligned, the energy is just slightly different than when they're opposite. And so that transition will emit the famous 21 centimeter, so deep radio wavelength of neutral hydrogen that revealed the galaxy to us when it was first used shortly after the Second World War. Okay, and we can use the electromagnetic, different parts of the electromagnetic spectrum to build a more complete picture of what we're looking at. So here's an example for the sun. So this is a spectrum of the sun. You can see that there's a peak around over here, and that actually represents what we can see. And then this absorption here, these are made by calcium atoms. This is a transition, an electronic transition in hydrogen. This is also hydrogen. This tells us that there's magnesium on the sun. The reason helium is called helium is that it was actually discovered in the spectrum of the sun. Being an inert gas, and very light, we don't see it much in terrestrial transitions. If you look at just the disk of the sun through a narrowband filter so that you don't burn out your optics and go blind, you might, if you're lucky and if you're near solar maximum, see a sunspot group. And if you look at the sun in a combination of ultraviolet and X-rays, you might see flares and activity emanating from sunspots like these. So these were not taken on the same day, but this type of flaring emission in the X-rays would be typically associated with a sunspot. So by looking at different wavelengths, we can learn a lot about solar activity, and this prints through to all kinds of other systems, like clusters of galaxies. So here's a galaxy cluster. Each one of these star-like points is actually a galaxy. And these galaxies are embedded in a gas, tens of millions to hundreds of millions of degrees, which is shown here as purple fuzz. And some individual galaxies actually have their own hot coronae. We call them coronae. So we can study these things together, and by combining X-ray, radio, and optical, we can learn something about what happens when two galaxy clusters, so each one of these clusters has a mass of about 10 to the 15, which is 100 trillion times the mass of the sun. There are hundreds of galaxies in every cluster, and every now and then they kind of fall together and merge under their mutual gravitational influence. And the galaxies miss each other. It would be very rare for an actual physical collision between stars to take place. But their gas interacts, and it gets even hotter, and you can see this blue X-ray bridge connecting these two clusters, and this purple here is radio. Reddish purple is radio emission, and this radio emission is produced by very high energy electrons gyrating in magnetic fields. This is called synchrotron radiation, and I'll be coming back to it again and again. So the highest energy photons are not on the diagram that I showed you. This is an image of our galaxy from where we sit within it, looking toward the galactic center. So this is the gamma ray sky. It was made with a NASA satellite called Fermi, named after Enrico Fermi. I'll mention him again. And you can see the galactic plane very sharply. You can see that the galactic center is very bright. You can see that there's just a little bit of residual emission, which seems to fill all of space. That's called the extragalactic gamma ray background. Cygnus X was one of the first binary black holes discovered. It's a massive star with a black hole in a mutual orbit. This is the Orion molecular cloud. There's a lot of star formation here and a lot of gamma rays. So these gamma rays are much more energetic than nuclear gamma rays by factors of 1,000 to 1,000,000. And we know of really only two ways of making radiation energy this high. One is from high energy electrons, and we can actually think of this as a collision between a photon and an electron. It's called the inverse Compton mechanism. So here's the electron. A low energy photon comes in, picks up some energy from the electron, and a high energy photon goes out. And this high energy photon can have as much energy as the electron did, which can put it in this giga to teravolt electron energy range. So that's one way. The other way is that two high energy protons can actually collide and interact, and they make unstable particles called pi mesons, and those pi mesons decay into energetic electrons, positrons, the antiparticle of the electron. They make some neutrinos, and they make some gamma rays. So is there any way of telling these two types of process apart? They're very different. One of them requires high energy electrons. One of them requires high energy protons. So so there actually is a way of telling them apart, and I'll get back later to what that is. Okay, so at this point, we've inferred the existence of extremely high energy particles, particles with many times their own rest mass, their Einstein E = mc squared energy, thousands or millions of times more energy than they would carry if they were at rest. So where do these particles come from? So this actually goes all the way back to the 18th century when Coulomb, so if you have any experience with electricity and magnetism, you might remember that there's a unit of electric charge called a Coulomb, named after him. And he discovered that air is partially ionized. And he found that out by making experiments with a so-called electroscope. So these are two leaves made of gold, and they're isolated here in this glass bell, and they can be given opposite charges, so they repel each other. And if there were no free charges in the air, they could just stay like this, in principle, forever. But they don't, they collapse. And that's what you would expect to happen if there actually were charges in the air, if some of the atoms and molecules in the air were charged. So this was a total surprise, okay? Because the fraction of particles under standard atmospheric conditions that have enough energy to ionize air is this number, 1/10 followed by 130 zeros, okay, extremely small number. So you don't really expect air to be ionized. Okay, so one of the reasons that this story has always stuck with me is it's a great example of how do you decide when some little detail should be followed up? And, you know, for scientists, this is a huge judgment call. You know, there were things that I just ignored that turned out to be very important. There were things that I thought were very important that turned out to be dead ends. And I did get a few things right. And, you know, we have to make these judgments all the time in daily life. And, you know, we have to ask ourselves, when is this really a legitimate question? And when are we just giving way to paranoia? Okay? So just saying. You're probably not sitting next to an alien at this moment or working with one. Okay, I see. I've exposed a fault line in this very congenial group.
Unintelligent life in the universe.
Okay, I'm not getting it. Okay, well, so the ionization of air was actually not forgotten. It was one of those things that people just didn't let go of. So about 100 years later, radioactivity was discovered. And so the hypothesis, or the question was, maybe radioactive elements within the Earth, which emit high energy particles, maybe they're causing this ionization. So it seemed plausible, and there was a way to test it. And the first test was to climb the Eiffel Tower, okay, and see, so carry an electroscope up to the top of the Eiffel Tower and see if it collapsed. Well, it did, it turned out, but what was decisive was ascending to a much higher elevation, which an Austrian physicist named Victor Hess did in 1911. He went up 5 kilometers in a balloon. Here he is coming down. This is a famous image. So he went up and he showed that the higher you go, the more ionization there is. So it seemed that the source of ionization was not deep in the Earth, but up in the sky. And they thought, well, maybe it's the sun. So he went up during a solar eclipse. He was lucky enough to be able to view an eclipse. And he got the Nobel Prize for this work in 1936. So that was really kind of good proof that the source of ionization came from the sky. So the source of ionization was dubbed cosmic rays. Now, the use of the word ray in physics is kind of like the use of the word itis in medicine. It means that, you don't actually know what it is. Like, arthritis, something is wrong with your bones. But what exactly? So in the case of cosmic rays, the question was, is it just an energetic form of light? Are they photons? Or are they actually charged particles? So the test that was devised to sort these two out was to exploit the fact that in a magnetic field, like the magnetic field of the Earth, charged particles will respond. Positively charged particles will circulate one way. So here are some images of particle orbits. Positively charged particles will go one way, negatively charged particles will go the other way. Turns out the size of the orbit depends on the energy of the particle. They're typically, very tiny for terrestrial applications. But it seemed that the cosmic rays were arriving mostly from the west, and this was consistent with them being positively charged particles. In other words, not photons, but particles of predominantly one sign. And it turns out that type of particle is a proton. So it took arduous effort and a lot of courage to do this experiment in that time. Here's a vessel rounding Cape Horn, climbing Mount Evans. I used to live in Colorado. This is a 14,000 foot plus peak. And this made big news. I like this headline from 1932 because it tells you of a time when science was considered really important. Science was considered front page news. Millikan, a physicist at Caltech, retorted hotly to Compton. He didn't just say, no, I think you're right. He retorted hotly. And this was on the front page of the New York Times, because there was a debate between these two great physicists about the nature of cosmic rays. It was a public debate that got a lot of attention. So years have gone by, and here's kind of a summary of some of the things we know. So we know that if you go into the interstellar medium, about one particle in a billion, or maybe even less than that, one particle in 10 billion, is a proton that's moving at almost the speed of light. It's called a cosmic ray. And the most energetic cosmic rays we've discovered, of which there are very few, have the energy of a well-hit tennis ball. So a single proton has as much energy as a killer serve. And to visualize what that might be like, if those conditions, that same conditions held in this room, okay, you take half the energy that just goes into making up the temperature of the gas, so it's about 70 degrees in here, so the temperature would drop to about 35 degrees, and the remaining, and the rest of that energy, the other half of that energy, would be in one particle in 10 billion with enough energy to do enormous damage to your tissue. Okay, so that's what it's like in the interstellar medium. It's not for the faint-hearted. So cosmic ray research turned out to be very fruitful and have a lot of branches. It is one of my specialties, but they're not all my specialties. So we can learn things about fundamental physics, like test, does light really travel? Is the so-called Lorentz invariance phenomenon that is the core of Einstein's theory of special relativity. That can be tested with cosmic ray physics. Particle physics, we've actually discovered new particles because the most energetic cosmic rays are many, many orders of magnitude higher than the highest energies that we can make in colliders on Earth. So there were particles that have only been discovered in cosmic rays. We've learned things about high energy radiation processes, like that decay of pi mesons into gamma rays. We've learned about that from cosmic rays. I tend to study sort of the effects of cosmic rays in other astrophysical systems, how they affect the galaxy, how they affect clusters of galaxies, and the branch of physics that I use to study these things is plasma physics. But this is just one branch or a couple of branches of cosmic ray research. So the UW is heavily involved in cosmic ray research. There's an observatory in the mountains of Mexico called HAWK, which stands for High Energy Water Cherenkov Detectors. So they just call it HAWK. So what is Cherenkov radiation? Well, it's kind of like a sonic boom, but for light. And it exploits the fact that when light propagates through water, it propagates more slowly than the speed of light in a vacuum. But you've heard that nothing can go faster than light, but if you read the fine print, what it says is that nothing can go faster than light in a vacuum. So if a cosmic ray, which is moving at almost the speed of light in a vacuum, travels through water, it emits radiation and it gets ahead of its own radiation, and it makes this kind of trailing cone behind itself the way a supersonic jet makes. This is a sonic boom. So the HAWK telescope consists of an enormous array of big tanks of water, and of course equipment to record the flashes of light that go on in there. And these are two UW graduate students who worked, physics graduate students who worked on these Cherenkov detectors, and in their copious free time, they spelled out HAWK in rocks. There was not, I guess, a lot to do at night there. Okay, so the other thing that the other aspect of cosmic ray research that UW is heavily involved with is the neutrino connection. And you may have heard that there's this ice cube observatory at the South Pole. How many of you have heard of ice cube observatory? Yeah, so.
I thought about applying.
They have an open positions. If you look on their website, they're eager. No, they're eager to hire. And you don't actually have to be one of the people who winters over. It's kind of a magical looking but bleak place. And so how do you catch a neutrino? They're called, they're called ghost particles for a reason. So these are detectors. If you go to the Physics Museum in Chamberlain Hall, you can actually see some of these detectors. Special drills. A special drill had to be invented to make a straight core 1 kilometer deep in Antarctic ice. And these strings of detectors are placed in there, and the neutrinos that they catch, and you'll see evidence for this in a moment, are actually neutrinos so this is down in Antarctica, they're neutrinos that came in the northern hemisphere and have traveled through the Earth to be detected by IceCube. We are hoping to, so there's an upgrade in process right now, and we're hoping for a next generation IceCube detector. So what can we tell from neutrinos? Well, first of all, sorting out the cosmic neutrinos from the sort of everyday neutrinos that are arriving constantly is difficult. This is a map, one of the most recently published sky maps of neutrinos. So this represents, this is not some galaxy. This is the 90%, this solid purple curve is the 90% confidence level for a single neutrino, okay? So these things are, they're just incredibly rare. And, we have fairly good positional information. You can see that all the detections are pretty much, except for a couple, pretty much in the northern hemisphere because of having to travel upward through the Earth. So what makes it worthwhile to go to all this trouble and expense to detect astrophysical neutrinos? Well, there are really two things. So one, neutrinos carry no electric charge. And that means that unlike the charged particles, which have those helical orbits that you saw in the Earth's magnetic field and the magnetic field of the galaxy, which I'll show you in a minute, neutrinos just come straight from their sources. So when a cosmic ray arrives at the Earth, its arrival direction is pretty much dictated not by where it was emitted, but by where the magnetic field of the galaxy has taken it, which we don't really know all that well. So neutrinos can be used to pinpoint roughly the location of a source. I'll show you an example of that later on. And then, unlike the gamma rays, so gamma rays are signatures of very high energy particles, but remember they can be either electrons or nuclei, and the neutrinos can only be produced by nuclei. So that's how we tell a source with cosmic ray electrons from a source with cosmic ray nuclei. So, yeah. Okay, let me say a little bit about the origin of cosmic rays. And I want to start by saying a little bit about the magnetic field of the galaxy. So this actually is from inside our galaxy, but this is an external galaxy, M51. This brightness here, this color map here just shows the brightness. This kind of tells you where the electrons are. You can see a spiral pattern, sometimes called the Whirlpool Nebula. And it turns out that when cosmic ray electrons orbit in a magnetic field, they produce polarized radiation, and the direction of polarization allows you to identify the magnetic field direction. So seeing the stuff in the first place tells you there's a magnetic field there, and measuring its polarization tells you how that field is oriented. And you can see that in this case, the magnetic field has kind of a spiral pattern. This is another detection technique. So this is right inside our own galaxy. Every one of these little segments, there's a background star that has been shining through interstellar dust, that pesky thing that obscures the Milky Way. And those dust grains have kind of an elongated shape, and they polarize the radiation when they're aligned in the magnetic field, and that tells us how the magnetic field of the galaxy is oriented. And you can see that most of these vectors are right in the galactic plane, but you can also see some loops and irregularities and so on, and this turns out to be a very good way of mapping the magnetic field. And pretty much everywhere we look that we might expect to see a magnetic field, we find one. And this raises the question of whether the entire universe was magnetized through some cosmological process, or whether these fields arose individually in separate objects. And that's just one more mystery that I've worked on. I might have talked about it when I was here 10 years ago. I never did figure it out. Okay, so when you put interstellar gas and magnetic fields together, and you're Enrico Fermi, you come up with a way that particles can be accelerated to high energy. That's called the Fermi mechanism. And he posited a bunch of kind of clumps, magnetized clumps that would be flying at random around the galaxy. And when a particle meets one of these things head on, it turns out it gains a little bit of energy, just as, if you unlucky enough to collide with a bus head on, you're thrown backwards. So it's thrown backwards a little faster than it went in. But an overtaking collision gives up a little bit of energy, and it's more likely that you're going to meet things coming toward you than that you're going to catch up with things running away from you. And that leads to a net gain of energy. So it turns out that the Fermi mechanism is most efficient near the shock waves that are driven through the interstellar medium by supernova explosions. Here's a famous image of the Crab Nebula. Here is shock-heated gas moving in. Here is a particle traveling along the magnetic field line. It collides, it comes back, it gains energy. The energy-gaining collisions predominate, and this does very well, actually, at reproducing most of the cosmic rays that we see. So, the Fermi mechanism is beautiful, but it can't be the whole story. So after years of trying one thing after another, we have still not cracked this sort of energy ceiling. There seems to be a maximum energy that this process can confer on particles, and it's not enough. We need to explain another factor of 10,000 to 100,000. And the only way we know how to do that and do it fast, which is the next part of or a later part of my talk, you really need a large electric field out in space. But I wanted to show you this image of the Tycho supernova remnant, which shows this thin blue rim of very high energy electrons that were accelerated in the shock. So this is the shock that this supernova remnant is driving into the interstellar medium, and it's made electrons that are so energetic, and the magnetic field has become so strong in this object that what comes out as radio in sort of ordinary parts of the galaxy is here coming out as X-rays, much more energetic photons. Okay, so now we've done electromagnetic radiation as a messenger, and cosmic rays as a messenger, and neutrinos as a messenger, and now we're going to get to the fourth messenger, which is gravitational waves. So according to Einstein's theory of general relativity, we shouldn't really think of gravity as forces. We should think of it as something that curves space-time. And we have direct proof that this happens through the phenomenon of gravitational lensing. So here's kind of a cartoon of gravitational lensing. We're observing this distant galaxy from the Earth, and the light emitted from that galaxy is passing through a very massive cluster of galaxies. And this cluster of galaxies is so massive that it has curved space-time a little bit around itself, and that causes light emitted from different parts of the galaxy to travel on slightly different paths. So what we would see from here, we would see one ray coming from here and one ray coming from here. And that's what happens to just light emitted in a single direction. And when you have a complicated object like a galaxy, it just gets sprayed all over the place. And you can say, well, okay, maybe this is just a galaxy with a funny shape. But there's this very characteristic pattern of arcs that we see. So this trail here is a galaxy that's been smeared out by the curvature of space-time around this galaxy cluster. And it's a way it's a way of changing the shapes of objects, and it can also be a way of focusing light. So it's turned into a very powerful cosmological tool. And I want to give you some idea of how huge gravitational energy can be. So if you turned off nuclear reactions in the sun and just asked how long it could shine on gravitational energy alone, the answer would be about 30 million years. But when a supernova, when a star collapses to form a supernova, it sends out about 100,000 times more energy, and that energy is released in 2 seconds. That's why supernovae are so bright. And if you merge 2 sun-like stars into a black hole, that releases about 10 times more energy than the collapse of one star. And that happens in about 10 microseconds. And these gravitational waves would have a wavelength about 0.3 of a mile. And if we think of a gravitational wave, a ripple in space-time, as being a change in gravity that passes over you, the length of a human body is so much shorter than 0.3 of a mile that you wouldn't feel much of anything. The gravitational radiation that you would feel would be very short wavelength that stretched your head maybe more than your feet. You may have heard of the phenomenon of spaghettification. That's what it is. Falling into a black hole, yes. Okay, so galaxies and galaxy clusters move. They move at about 1,000 kilometers a second, but the distances are so vast that the gravitational field of a galaxy cluster really doesn't change very much over the human lifespan. But if we look at particles like binary stars or even planets moving around stars, the gravitational field exerted by them changes very fast. And changes in the gravitational field are transmitted at the speed of light. So if you suddenly plucked the sun out of the middle of the solar system, we would know at about the same time, exactly the same time we saw it disappear, 8.5 minutes later, and then we go flying off into space, there would be no sun. So this is actually a depiction of what is happening even to the Earth in its orbit. So the Earth is, as the Earth moves around the sun, that changing gravitational field is creating gravitational radiation, and that gravitational radiation is carrying away energy from the orbit. And the result is that the orbit is shrinking. Now for the Earth-Sun system, this is a very weak effect because the Earth is so far from the sun. And it actually, if you can estimate how long it would take the Earth to fall into the sun due to emission of gravitational radiation, and it's about 4 times 10 to the 23 years. Now the universe, for comparison, is about 10 to the 10 years old. Okay, so we have other things to worry about. But For closed binary systems, we've actually seen this happen. So now we can combine these messengers to kind of follow the energy. You know, so sometimes they say if you want to understand current events, follow the money. Who benefits? In physics, we follow the energy. So energy from merging stars or supernova explosions or matter falling into a black hole, all these three things. So this is the Event Horizon Telescope image of M87, Tycho supernova remnant, which I showed you before, and this cartoon of a gravitational inspiral. Some of that gravitational energy gets turned into magnetic energy. So a magnetar is a very strongly magnetized neutron star that is sometimes left over when a supernova explodes. And this supermassive black hole in the center of M87 is actually, on large scales, a very powerful radio source that's sending out these huge jets of relativistic plasma. So some of the energy that comes from gravity gets turned into electromagnetic energy, and some of that energy then gets turned into particles, cosmic rays, neutrinos, and photons. And so for things that happen very fast, these are all going on at once. And can things ever happen that fast? Yeah, this is just a close-up of how some of these processes could work. On November 3rd, 2022, not that long ago, IceCube gave a press conference. And it was a multi-messenger science press conference. And they announced that they had found a neutrino coming from an active galaxy. And if you actually do the statistics, this means something. And what it means is that an active galaxy, which is accreting material falling into the supermassive black hole at the center, is also making neutrinos. So our ideas that black hole accretion disks are kind of factories for making high energy particles is, it's confirmed in this new way by discovering neutrinos. And of course, we hope to discover more. But let's talk about things that happen really fast, because these are some of our greatest challenges. So in 2011, the Crab Nebula, which I showed you an image of, was found to flare. And so this is kind of the flux, the energy per time of gamma rays that came from the flare. These are in Julian days, so it's a fairly long interval of time. I'll show you some shorter ones. But there are these peaks here of enhanced gamma ray emission. And these photons are so energetic that they must come from cosmic ray electrons, given the environment of the crab. And the only thing we know that can energize electrons that quickly and then cause them to lose their energy, so the energy goes up, the light goes up, and then it goes down, is the rotational power of the neutron star that's somehow extracted by electromagnetic fields. So these Crab Nebula flares inspired a lot of research, and actually also a laboratory experiment done by a friend of mine. So I took a little break this morning when I was working feverishly on this talk to read Science magazine, which I get every week. And there was actually an article that in today's issue of Science magazine that's perfect to tell you about in the context of this talk. So fast radio bursts are exactly what they say they are. They're intense bursts of radiation. They were only discovered a few years ago, I think less than 10 years ago. We don't really know what causes them, but I want to call your attention to the extremely short duration of this burst. So this is milliseconds. I don't know if you can see this. This whole interval here is 30 milliseconds, 30 thousandths of a second, and the burst occupies only this small part of it, really just a few thousandths of a second, this huge spike in radio emission. And the reason this got published in Science magazine, which is very difficult to publish in, is that they saw the polarization of the radiation change at different frequencies over time. And that means that the magnetized plasma, that this radio radiation, wherever the source was, if the source is embedded in very turbulent plasma with a churning magnetic field, the polarization can change that quickly. And in fact, that's the explanation that they proposed. They couldn't think of any other. So this is a very rapidly changing field, and explaining these observations is going to be a huge challenge. It was only published today. So fast radio bursts may be associated in some cases with gamma ray bursts, which are very short duration, intense bursts of gamma rays. How short? Well, this is time in seconds, and you can, so here's your burst as a function of time, up, down, fractions of a second, again, immensely powerful gamma rays. So these gamma ray, so when I was first coming up in the field, gamma ray bursts had just been discovered, and they seem to come kind of from everywhere on the sky with equal probability. And that was thought to be a clue as to what they were and how far away they are. So if you remember the Fermi image of gamma ray emission, you can really see the disk of the galaxy in it. You can, most of the radiation is coming from the galactic plane. But gamma ray bursts really come from pretty much everywhere on the sky. This is 2,704 gamma ray bursts detected with the BATSI instrument on the Compton telescope. They're color-coded for brightness. The brightest ones are the red ones, but there's really no gaps. They come from everywhere. So what does that mean? That either means that they come from very far outside the galaxy, or from very, very close to the sun. Because, you know, imagine that these bursts were in our solar system or something. Then, you know, they come from anywhere within the heliosphere. There wouldn't be any preferential direction. Same is true if they just come from the, you know, anywhere in the universe. But if they come from, you know, if they're sort of typical galactic sources a few thousand light years away, they should be confined to the galactic plane because other forms of emission are. So this is a powerful clue, and we've now resolved that they come from cosmological distances. So this is a gamma ray burst with X-ray light echoes around it. How are these light echoes produced? Well, what happens is these gamma rays are emitted in all directions, and as they come to us through our own galaxy, some of them are scattered and re-emitted as X-rays, and because they've been scattered, they go on to different paths, and they take different amounts of time to reach the Earth, and that produces these echoes. And as we go further, so they saw 2 echoes, and there might even be or have been a third echo over here, even farther away, coming later and being fainter. So what are these gamma ray bursts? What is causing these gamma ray bursts? Some of them never show up again. Some of them are repeaters. And then in 2016, the Gravitational Wave Observatory, LIGO, in Hanford, Washington, published, I won't say detected because they actually sat on this thing for years trying to figure out if it was real, published the first observational evidence of a merger of 2 black holes. And they interpreted this, so this yellow thing, this predicted, is what you would see if 2 black holes, each one about 30 times the mass of the sun, spiraled together. What would you see? You would see radiation of increasing intensity as they approached each other, and shorter wavelengths. And so Livingston, Louisiana saw the same thing. Virgo in Europe actually saw the same thing. Here is the first and so far the only example we've seen of 2 merging neutron stars. What was the most important difference between these two events is that here we only saw gravitational waves, no other cosmic messengers, no evidence for any other cosmic messenger. Here, when two neutron stars merged, we saw a lot. Here's the gravitational radiation from LIGO. Here are two different gamma ray satellites. Integral is a European satellite. Fermi is a US NASA satellite. And they saw this gamma ray emission. And radio emission was also seen, but I don't have an image of it. Now notice that these two things are not at exactly the same time as the in-spiral. So the gamma ray burst actually came after the two neutron stars merged to form a black hole. Why is that? The span of time covered by this binary black hole merger is only 0.2 of a second. Okay, this last burst of gravitational radiation, it took eons to get to that point, but once they did, it happened very fast. So again, here are some examples of what happens when we follow the energy. Gravitational energy, electromagnetic energy, and particle energy. And we're learning how to put all these signals together and decode what's actually going on. So here are my last words. This is a strawberry poison frog from an article in Nature magazine. And this is a tadpole. This is a mother, okay? It's almost Mother's Day. And this is a mother that only a mother could love. And she's carrying her tadpoles. And so throughout the long time that I've been in this field, there's been this kind of leapfrog process where sometimes there's a new technology developed, like how do we, so, you know, x-rays, you have medical x-rays because x-rays go through stuff. So how do you make an x-ray telescope? How do you make a gamma ray telescope? How do you make a neutrino detector? How do you detect a cosmic ray that has as much energy as a well-hit tennis ball? So there's technology development, and sometimes that comes first, and then the theory and the computation catch up, and maybe they go a little beyond what the technology development has allowed us to see, and that spurs further technology development. And so we're living in a time where the pace of new discoveries is really breathtaking. And I don't think we'll ever run out of new discoveries and new problems. And keep looking. Thank you.
Just a quick question. What energy level pathway do you think might have created all the dark matter, or if that's even how it would happen?
Oh my gosh. So in the spring of 2018, I heard a lecture by a prominent cosmologist who said that if the dark matter particle, if the nature of dark matter were not discovered in the next 5 years, it would be a crisis for physics, okay? This is May of 2023. He has not announced a crisis, but we still don't know what the dark matter particle is. We're pretty sure we know what it isn't. So, you know, there used to be all these ideas like burned out stars. It's not burned out stars. Doesn't seem to be massive neutrinos. It's a particle that we don't know. One candidate is something called an axion. And there may be a way of looking for axions in neutron stars. And this team of people that I showed in the lower right-hand corner, if I can go back to it, of my introductory slide, that's kind of one of our schemes. So this team that I showed you is kind of an aspirational team in the sense that we wrote a big proposal for money to work together, and we haven't heard yet if we're getting it. But if we do, this is one thing that we're going to try. So yeah, I don't know. There was an idea that So there's a kind of more gamma rays coming from the immediate center of the galaxy than was expected. And there was an idea that this could be produced by the decay of dark matter into particles that then produce gamma rays. And that was kind of a live idea for many years, but we found another explanation for those gamma rays. It just seemed to come from pulsars that we didn't know were there. So, yeah, I don't know. It's one of those things that I have to forget about, because otherwise I would just torture myself with it.
Ellen, when you talked about that recent discovery that the smoke, the radio burst,
yeah.
Is there any theories in terms of, or any information in that documentation as to if the polarity flip is a flip one way and then back, or is it staying flipped?
Oh, yeah, that is a great question. So this is the only example of this that has so far been discovered, and it's one flip.
One flip.
It's one flip, but this is a repeater. This is a repeater, so I think this source is going to be monitored extremely closely.
Because that could be a clue to the source.
Absolutely, absolutely. Yeah, it's a very exciting development.
We've lost the battery here, so go ahead and take the question. Just summarize the question.
Yeah.
I was wondering about that ice cube station, and I was wondering, what is it about Antarctica that makes it a good place to catch
There's the
neutrinos?
clarity of the ice.
That's a great question. So the original, there was a pre-proposal before doing it in Antarctic ice. There was a project called DUMAN, Deep Underwater Muon and Neutrino Detector. Okay, our field runs on acronyms, and the idea was to put detectors similar to what I showed you in the ocean. And the ocean environment is too complex and too corrosive. But actually, one of the spin-offs of IceCube has been the best study, really, and characterization to date of Antarctic ice and its material properties. And it does turn out to be good. And, you know, I worry about climate change, to tell you the truth. How long, yeah. And, you know, and I've brought it up with people, and they don't seem to be worried, is all I can tell you.
It'll take a while to melt down that far into the...
I guess, but, you know, things have a way of kind of breaking off and...
Yeah, the edges of the continent the glaciers are getting to fall into the oceans. But, you know, the ice cube is right near the...
It's at the pole, yeah, I plan to have.
I have a two-part question, totally different subjects. One on the picture of Tycho, the supernova. The stretching from 2 o'clock, or noon to 2 o'clock, there is a bright white line. Is that significant, or is it an artifact?
Oh, yeah, that is a great question. So is the white line on the Tycho supernova remnant, what is that? And the answer is, there is an answer, and I don't know what the answer is. I assume you're referring to this,
Yes.
this feature. Yeah, I don't know.
The other question is, they're also building a neutrino telescope in the Mediterranean, aren't they?
Yeah.
And the question is, why are they able to see? Isn't the Mediterranean kind of messy?
Yeah.
And so how are they getting around the messiness there? And isn't there another project also in the Pacific? Am I wrong?
So they're back to, so I don't know what has changed since the 70s, which is when DUMAN, you know, that was sort of the prime of DUMAN. I don't know the answer to that question about what makes underwater technology favorable now.
But they're still working on the...
I think so, yeah.
Can you explain why IceCube more likely will detect neutrinos coming all the way through the Earth?
Yeah, so we are constantly bombarded by neutrinos, and most of those neutrinos are produced by the breakup of cosmic rays in the atmosphere. Okay, and they have to be sorted out from the true astrophysical neutrino, the astrophysical neutrinos from distant sources that arrive by themselves. And filtering the whole mess through the Earth is a way of cleaning that up. So we do get, so in Antarctica, we do get the astrophysical neutrinos that just have come directly from through the southern hemisphere, but it's harder to tell what they are.
You can't sort them out.
Yeah, yeah, exactly.
Oh, are there any more questions for Alan? Well, great presentation and very
Well, thank you.
fascinating broad overview.
Thank you.
We're all very lucky to be here tonight and witness your presentation. So, on behalf of Madison Astronomical Society, I would like to present you with this token of our appreciation. Some years ago, she got a coffee cup, so we wanted to make sure that she got something different this time.
What I'm going to do is I'm going to make this a little bigger since I have hair.
You do?
Avoid hair.
Hey, there you go.
Well, hope to see you again here some other time.
Well, I don't know if I have 10 more years.
No, I don't have 10 more years either, what I'm doing, so.
Cosmological time.